Okay, so in this video, again, nothing really new. We're just going to do some example problems, some ways that we can see the net change theorem in action, otherwise known as the fundamental theorem of calculus, part 2. So let's start with example 2. A fitting number for the fundamental theorem of calculus, part 2. And that says, given a velocity function, and let's say this velocity function is v of t equals 3t minus 5, and that's given in meters per second. So given this velocity function for a particle between 0 and 3 seconds, I'm going to ask you some questions about this, starting with part A. So we know the velocity function. We know velocity is the rate of change of position, and we know acceleration is the rate of change of velocity. So that we have that relationship between position, velocity, acceleration with derivatives, which means, of course, that we have the backwards relationship between those three quantities in terms of integrals. So in part A, find the net displacement. So remember, what is net change? Well, we got this net change theorem, fundamental theorem of calculus. We have the net change theorem that says, well, if I want to know the net change of a function, all I have to do is integrate its derivative. So we want the net change of the position function. So we find it by integrating derivative. And what's the derivative of position? Velocity. That's all we do here. So we know that the displacement between 3 seconds and 0 seconds is going to be the integral from 0 to 3 of that velocity, which looks like that. And as soon as we use the net change theorem that way, we just evaluate with fundamental theorem of calculus, and we're going to go on. So we can do that blue way or that green way, up to you. So let's do the blue way, since I think it's more common for a lot of calculus classes. But again, both ways are fine. Let's calculate that antiderivative at any rate. And we'll get power rules saying add an exponent and divide by the exponent. Remember, the 3 is just a constant multiple. Just stays there out in front. There are a bunch of integral properties that you can use if you want to take some extra steps and really show where all this is coming from. And they get minus 5t like so from 0 to 3. Plug in the 3, plug in the 0, find the difference, and we're done. So we plug in 3, we're going to get 3 halves times 3 squared minus 5 times 3. Minus, when we plug in 0, we're going to get 3 halves times 0 squared minus 5 times 0. You might say, Jason, you're writing behind your head. Don't worry, because everything over here just becomes a 0 anyway. So it's like my head is giving you the answer. Like people call a 0 an egg. People call bald people eggs sometimes, which is not usually very nice. But there you go. My head's giving you the answer. And that brings us to just simplifying the first half, because the second one's 0. That's going to give us 3 halves times 9, which is going to be 20, which I'm not going to skip a step because I've been making a lot of mistakes in my head recently. 3 halves times 9 minus 15. That's going to be 27 halves minus 15. So that is 13.5 minus 15, or negative 1.5. Now, you might be alarmed at this point. You might be alarmed and say, negative, first off, we need units. They say negative, that doesn't make sense. What are we talking about? But if you remember what we're talking about, it actually does make sense to have a negative as an answer. We have a velocity. Velocity can be positive and negative. Positive usually meaning forwards, whatever we define that to be, and negative being backwards. Maybe forwards is up, backwards is down, maybe forwards is right, backwards is left. Our velocity in this case, if we're looking at the interval from 0 to 3, should be negative sometimes and positive sometimes. And we're looking at net displacement, not distance traveled. Distance traveled should always be positive, but net displacement can be negative. If it's a negative number, maybe that means we are negative 1.5 to the left. What are our units here? If velocity is in meters per second, our displacement should be in meters. Okay. That's what we're going to have here, negative 1.5 meters. So that's our displacement. If there were more context, you could say 1.5 meters to the left, 1.5 meters down. There's not really any more context here. So we're just going to say negative 1.5 meters. But whenever possible, try to interpret that negative in the context of the problem. Or if it was money, we could say we're losing $1.5 or something like that. So that's the idea. We can check our answer because goodness knows it's one of those days for me and I would really like to check my answer. So if we look, we go the integral from 0 to 3 of 3t minus 5 dt, and that's negative 1.5. Thank goodness. Okay, let's do part B. That's the net displacement on this time interval. And part B is asking us, okay, that's the displacement. What's the total distance traveled? All right. Find the total distance traveled on this interval. So now we should expect this number to be bigger. On this interval, not integral. Right? If sometimes we're going backwards and sometimes we're going forwards, the total distance we've traveled should be more than the net change. And remember back, we talked about two things, net signed area and actual area. We said one was the integral and one was the integral of the absolute value. And total distance traveled is that same thing. So displacement is just going to be the integral from 0 to 3 of the velocity. Total distance traveled is going to be as covered in 1.2 or 1.3. I think it was 1.2. The integral from 0 to 3 of the absolute value of the velocity. Because remember, absolute value of velocity is the speed. Integrating absolute values is tricky business. And in fact, most of the time, all of the time to my knowledge, we just don't do it. We say, all right, absolute values, no good. Let's get rid of them by finding when is the function positive and when is function negative. Because this function, every absolute value function, the absolute value just makes, instead of it going negative, just ends up bouncing it off the x-axis. And we'll do it like we've done earlier problems. So this is the integral from 0 to 3 of the absolute value of the velocity function, which is 3t minus 5. So we need to find the area under this curve, which will be, of course, always positive. Now, in this case, it's pretty easy to graph it, but sometimes your functions are going to be messier. You're not going to be able to graph them as easily. So what you're going to want to do in those situations is find when the inside is positive. And to do that, because it's a continuous function, the only place it can switch between positive and negative, if it's a continuous function by the intermediate value theorem, is when it's 0. So it's continuous, so it can only switch, only go from positive to negative when it equals 0. So a lot of times that's when we find. We find when it's 0, and that basically tells us, well, it's positive everywhere on one side of that and negative everywhere on the other side, or maybe there will be a bunch of intervals. Just like, remember the first derivative test in Calc 1. We did the same process all the time for that. We said, well, it's if the first derivative is positive, the function's increasing. We want to find out where the function's increasing. We want to find out where the derivative is positive. Let's find all the places it's 0, plug in test points, and we did this exact process. So this one will be a little easier. 3t minus 5 is equal to 0 when t is 5/3. And then we could set up a little chart and say, all right, at 5/3, it switches at 0. What happens to the right? Well, to the right of 5/3, 2, for example, we plug in 2, we get that it's positive. To the left of 5/3, we could plug in 0, for example. If we plugged in 0, we'd get something that's negative. And we know it has to be positive on this whole interval. We know it has to be negative on that whole interval because it's continuous. And the only time a continuous function can switch is when it's equal to 0. And the only time it equals 0 is at 5/2. So we can write this now. Split this up into two integrals. The first part before 5/2 plus the second part, which is after 5/2. Thirds. 5/3. So it's positive on this second interval, right? It's positive to the right. If it's positive, the absolute value becomes redundant, and we just get this. If it's negative, if we know something's negative, then the absolute value of it is just the negative value. And in fact, that's one way, if you remember the absolute value function, is defining it as a piecewise function, where if the inside's positive or 0, then the absolute value is just the inside. And if the inside is negative, then it's just negative of that inside. And that's exactly what we're doing here. We're just adding a negative in front of the function. And now that's how we deal with the absolute value. It's really just using this, the definition of the absolute value function, and finding when our function's positive and when it's negative. Again, this is a linear function, pretty simple function. You can do this problem a lot of ways, but this blue method is very important and useful when we deal with messier functions. So that's why I wanted to make a comment on it here. And now we can just go to town, integrating. There's a couple of ways that we could deal with this. I want to deal with this negative first. Let's write this as 5 minus 3t, distribute that negative. And in the second one, you could either do the next step or wait. I'm going to wait so that both of our integrals are proceeding at the same pace, but you don't have to. And now you just go on solving them out. This is a good opportunity to practice your algebra and your arithmetic. Pause the video, try to get the right answer, and see if we get the same thing. And I'll run through it rather quickly in the meantime. This first one becomes 5t minus 3/2 t squared. We're evaluating at 0 and 5/3. And the second one is going to be 3/2 t squared minus 5t. And we're evaluating from 5/3 to 3. Now to keep things moving, and I'm just going to plug these into a calculator to get this final answer. And we're doing an application, so we might need to do an approximation. But anyway, what we have at the end of the day should be as follows. I'm going to type this in. The integral from 0 to 5/3 of negative 3t minus 5 dt plus the integral from 5/3 to 3 of 3t minus 5. With respect to t, you add those together and you're going to get about 6.83. We were asked about total distance traveled, so we're going to say about 6.83 meters have been traveled. And now, after we finish the problem, let's look at this graphically and see another way what's happening is happening. So we're looking at a velocity function. It's 3t minus 5. Okay, and we're specifically looking from the interval from 0 to 3. On this interval, we're ranging from about -5 to something a little bigger than that. Okay, 0 to 3. We're looking at this interval. Of course, we have this negative area and this positive area. So the displacement is just the positive area minus the negative area. The negative area is bigger here. That's why we had negative 1.5 as our displacement. Now, distance traveled is just the sum of the areas. So treat this area as positive, treat this area as positive, and add it together. And in fact, what we did is we integrated the absolute value of this velocity function, the speed. That's adding these two things. They have the same areas, just now their areas are both positive. And again, if we actually wrote it out as the integral from 0 to 3 of the absolute value of 3t minus 5, we would get the same answer. Okay, just always make sure, check your arithmetic. Very easy to mess that up. Okay, so this area is going to be much bigger in this case. And it will always be bigger if the function is ever negative. And depending on how often the function is negative, there will be a much bigger difference between the displacement and the distance traveled. So that's what's happening in this problem. Let's do another one, example 3. If a motor on a boat is running and consumes gas, at a rate of 5 minus t cubed gallons per hour, which seems a little weird to me. I don't know too much about engines, but I would not expect the gas rate of consumption to be cubic. I would think it would be kind of close to constant, but who knows? How much gas? Wait, what? Did I write this problem down wrong? How much gas is used in the first 2 hours? So here's the reason why I'm wondering whether I copied this problem down wrong. Because look at this. Just think about this. What this is saying is at the very start, we're using 5 gallons every hour. But after 2 hours, how fast are we using gas? T is 2, 5 minus 8. After 2 hours, we're burning gas at a rate of negative 3 gallons per hour. I guess maybe we're filling up the tank at that point. This seems a little fishy. Let me just double check the original problem. I'm taking these from the book. And nope, that's what it wants. Let's ask a different question. How much gas is going to be burned in the first hour? So at the start, we're using gas pretty fast. 5 gallons every minute. After an hour, we're using gas a little slower at 4 gallons per hour. Or if this were a squared, it would have also worked in the original problem. Okay, so we're using gas a little slower. So start is 5 gallons per hour. At the end, 4 gallons per hour. So we can get an estimation, right? On average, we can just really roughly estimate that we're going to use about 4.5 gallons of gas. But this is an example for us to find the exact answer, assuming this is true, using calculus and a little bit more practice. There are more applicable examples in the homework, and we'll be doing those in later videos. Yeah, I wonder what happened here. All right. Maybe it's the textbook being quirky. Maybe I misunderstood the problem. Anyway, the total gas used is just going to be by the net change theorem. Again, we can think of, well, we don't have to think about it with function notation. We can actually just say the total used is just the integral of the rate of change. The net change is just the integral of the derivative. The net change in gas is the integral of the rate of change of using of gas. And the rate was given right here. Now we can calculate things this way. We're going to get that the antiderivative is 5t minus a quarter t to the fourth using the power rule. We'll evaluate that at 0 and 1. When we plug in 1, everything turns into 1s, and we get 5 minus a quarter. We plug in 0, everything turns to 0. We got the nice hint right here for the second part. With the egg, I'll get 4.75. So our quick gut estimate, this is in gallons, was saying, well, we started at 5, we ended at 4. Just, find the average and say we're doing about 4.5 gallons every hour. So estimating about that much burning. But because this is a cubic function, we're actually much closer to 5 gallons per hour than we are to 4 gallons per hour for most of this, right? Because we have this, really this function has like this sort of curve. So we're more above than behind or than below, and we'll get 4.75 gallons total. That's how much gas we're burning in that hour. And then after that, weird things happen with this function. Still not sure exactly what the book wanted with this, but there we go. We got some practice anyway. Let me know if you have any questions. And in the next video, we'll talk about something new that we'll use in the future with even and odd functions that we can use to make our lives easier. Bye-bye.